Okay, well, thank you. Thank you so much. Again, like to echo Sandeep's point. Uh, Thank you, all the speakers, and mostly Sandeep and Hari for doing all the real hard work for making this happen. Okay, so I'm going to use chalkboard primarily because I've been lazy putting together the slides. Um, this is also an opportunity for me to uh, advertise a monograph that I wrote, for which I make zero money, because this is one of those things where there's no royalty associated with that. So my soul is clean here. But I'm primarily going to walk through uh, a collection of results through this. And for that reason, me not having slides makes me a little better because all the details are here in case you are interested. And it should be available freely via PDF if you want it. And if you can't find it, please email me. I'll send you the PDF. This is a monograph that I've written with George Chen. George Chen was a graduate student at MIT. I had a pleasure of co-advising him with my colleague, Polina Goland. He's now professor at Carnegie Mellon University. So here is the outline of my talk. So first I would, let me see. So first I'll just walk through introduction, our reasons of why we wrote this monograph, and what is the history of the topic, what are the exciting things that are out there, and just a perspective in terms of why this class of algorithms, that is nearest neighbor algorithms, are really, really interesting, especially in the modern times when we're all thinking about deep neural networks. Okay, so I'll sometime here, hopefully no more than 10 minutes. Then I would like to set it up, discuss what the problems or prediction questions that are of interest, and discuss the algorithm. Okay, and then there are two classes of problems we'll discuss here, and primarily I'm going to focus on regression. So there's prediction problems, supervised learning, regression, and classification. I'm going to focus on regression because here I will argue that actually classification reduces to regression. And I'll define precisely what I mean formally in terms of that reduction. So that means all we need to worry about is regression. And then what we'll do is we'll spend time trying to understand how to analyze this class of algorithms for regression problems. Now, one may ask the question, and as I'll go through the history, this is in a sense more than 1,000 years old, and then sort of as far as math is concerned, at least 70 years old, and there's like two. I would say in non-parametric statistics literature, this has been beaten to death. So why am I sort of talking about it right now in 2019? And because there's extremely simple proof that I can actually teach in this setting. So I want to walk you through that proof, and it's in a sense, it's most general, and despite generality, it doesn't lose much of an optimality. So it's concise, and there was a reason why we wrote this monograph. While we were trying to go through a bunch of applications and all complicated proofs with all sorts of assumptions, and this is kind of assumption-free, simple, unifying, and that's one of the reasons why I would like to go through that in detail. I will skip classification, as I mentioned, because of the reduction that will come here. And then finally, I would like to talk about some of the challenges in terms of operationalizing some of these algorithms. In particular, the three things I would like to discuss is, and this will make more sense as we talk more about it, how many neighbors or how to choose number of neighbors. Computation issue. There's a beautiful literature that is interfaced with theoretical computer science, computational geometry, and actual implementation in terms of large scale. And then finally, how to decide on distance. And again, this will make sense. And for each one of them, I'll tell you about, primarily, these are the three directions where there are lots of exciting questions that remain open. So I'll tell you one very recent algorithm that came out a year back, and in a sense that's not fully analyzed. I'll give you a toy model where you can analyze and argue that actually it works really, really well. So those in the audience interested, try to sort of argue why this should work in general. The general framework where we'll discuss here. Computation, again, I'll sort of, it relates to approximate nearest neighbor indices. Beautiful theory out there, but in a sense, we've just scratched the surface despite 20 years of very active work in this. And then finally, how to decide distance. This is where one example in context of matrix estimation, I'll explain that there is a natural way to decide distance. But again, more generally, question remains open. And I've got my own favorite algorithm for this that I would like to suggest. I don't know how to start even analyzing about it. It's actually meta algorithms. I don't even know how to write down precise algorithm. So hopefully some of those in audience would enjoy that as well. And that, my hope is that would take all of my time. If I go over time, I will stop earlier. If I go under time, that was exactly the amount of time I wanted to speak. Okay, so with that, let's get started. Okay, so introduction and first, I mean, this is something that sort of I read somewhere when we were we started reading through a massive amount of literature on nearest neighbors, and somebody sort of wrote, I don't remember who, that things that appear similar must be similar. Well, we replaced it in our text saying that things that appear similar could be similar, may be similar. So with that, in a sense, in more recent examples, Nate Silver, the 538 fame, he in 2003 argued that you can use nearest neighbor style methods to predict performance of baseball players. And he showed that it got him much better accuracy than other methods empirically. And then in 2008, when he sort of wrote down the very clearly the blog and 538 showed that sort of some variation of nearest neighbor algorithm is used for better accurate forecasting of elections / polls / whatever. Okay, so those are some of the few popular examples. There was a nice paper by Criminisi and again, so this is just a random collection of applications that I'm choosing. It's just to give you a flavor. In 2004, Criminisi used nearest neighbor style methods to do what I would call image in painting. That is, suppose you have an image with some of the missing pixels or noisy pixel, how do you denoise that? And he used the image in painting across images or population of images. George, for example, in his thesis used nearest neighbor method. It was 14, 15. Nearest neighbor method to use to do identifying organs in MRIs in an automated manner. And it's what's called patch-based image segmentation. And this surprisingly worked really, really well. It's very simple nearest neighbor algorithm. He also, in his thesis, tried to use this for Twitter trend prediction. And in a sense, some of these early applications got us to looking at the literature in terms of understanding, okay, what are the theoretical guarantees available? How do people think about them? What is the generic framework? Is there a clean unifying theorem that's out there? And for lack of thereof, we decided to sort of just put all the understanding that's out there and summarize it in some succinct form. So really, in a sense, what I'm going to talk about, we have no contribution really other than just understanding sort of the literature and trying to condense it in some one form. In the process, we thought that sort of we found some form of new result, but that's kind of relevant because really there's a simplest statement at least that's out there now. Yeah. Yes. No. So I think when I mean nearest neighbor method, I mean generic nearest neighbor method in the k nearest neighbor method, the distance limited nearest neighbor method or kernel method. And I will sort of keep the exposition to the nearest neighbor method to keep things simple, but all of those things are sort of just naturally extended that's discussed here. Now, these are some of the recent examples, but if one wants to go to the oldest nearest neighbor example, then we came across this nice paper written in 2014, forget the name, which actually found the reference to the work of Al-Hazen, or Al-Hazen is a Western word. Al-Khalili is the original way of speaking about him. This is a famous scientist who wrote 6 volumes of book. In case you don't know, just Wikipedia him. He's got, at least he used to have a beard as per the Wikipedia. He grew up in Iraq and then was jailed in Cairo at some point of time. And people believe that while he was jailed in Cairo between 1011 to 1040 or something like that, he wrote a book, or rather, what's called Book of Optics. And the idea there was that how do humans recognize objects? And so the theory before that was that eyes throws the light, and it's kind of now in hindsight it's silly, because if it's dark, where is the light? But anyways, so that was the theory before that. His view was that no, actually light enters and then there's an impression that it makes, and through that we recognize it. Then the one intellectual challenge for him itself was that, well, in a sense, eye is like a pinhole camera. So he's also attributed to the discovery of pinhole camera, or invention, whatever. Yeah, invention of pinhole camera. And so if it's only one thing is coming, how do you recognize the image? And his explanation was very simple, that, well, first time you see something, you don't recognize it. You see over and over again, your brain forms the memory of it. And then next time you see again in a sequence of things, now your brain recognizes through nearest neighbor search that it must be that. Now, this was kind of a theory. Okay. Now, amazing thing about this is that not in the context of visual, but in the context of sensing odor. A bunch of biologists did the experiment around San Diego in 2017, along with Das Gupta. Sanjoy Das Gupta is somebody who who has done important work in this domain over past couple of decades. He, along with the biologists, they did experiments in fruit flies, and they argued, to the extent possible in the context of biology, that fruit flies do have neuronal circuits which try to recognize odors through nearest neighbor. And in particular, they are trying to do that nearest neighbor recognition through hash functions. The type of hash function, at least a variation of hash function, is what people use to build nearest neighbor indices efficiently. Okay, so that's lots of interesting things that have happened in history. So the question is that, okay, so those are the algorithmic history. What about, and successes? What about the theory? And which is what I want to talk about here. One of the earliest reference in terms of anything concrete analysis-wise is by Fix and Hodges. So there's a long history here. So Fix and Hodges in 1951-52, through a bunch of unpublished manuscripts that at least formalized the question and had some initial analysis. Then Tom Cover at Stanford and Hart, who was a student. So they, in 1967, wrote really interesting paper where they argued that in large sample limit, asymptotically, the classification error of one nearest neighbor, and I'll define that more precisely, is no more than, so classification error of one nearest neighbor is no more than, in terms of classification error, 2 times the best classification error you can get. And that will be just a Bayesian, for Bayesian classifier. And then there was a very nice story that sort of Tom, I think, wrote in that manuscript itself, that Hart and comes to Tom's office saying that, hey, we're using something like nearest neighbor to do some classification. Empirically, it works beautifully. And the Hart and Cole was another student, and finally Hart and Tom ended up writing a paper. Now, around the same time in computer science, Knuth formalized this question of finding nearest neighbor things as a what's called post office problem. If you are an information theorist, you know nearest neighbor really well, because that's what you do in ML decoding at the end of the day. And well, I mean, since 70s, post Knuth writing down post office problem, there's a lots of work in trying to build data structures to find approximate nearest neighbors. All right, so that's as much as history I wanted to cover. And before I get started in terms of setting things up, there are a few reasons why I believe that nearest neighbor algorithms are terrific. And they are as follows. So I would say roughly 4 reasons. One is, well, it's, okay, so let's say there are 4 reasons. 1, 2, 3, and 4. Let me make sure that I speak in the right order. Okay. So I would say one is flexibility. The second is computational advances. The third is what I would call non-parametric. And the fourth is interpretation. And in some sense, let's say, confidence. Okay, so what do I mean by flexibility? As we'll define, in nearest neighbors, it's a meta algorithm. It's not an algorithm, because you decide what distance you want to use, and then of course parameters are parameters. And that flexibility means that you can go across domain really, really well, and it sort of generalizes very nicely. And of course, it's very simple and intuitive, so it's easy to think about. It's not complicated. There is no voodoo involved there, other than, of course, the distance. The computational advances, there's lots of computational advances that have happened since 70s in terms of building nearest neighbor indices or data structures. And that makes it really easy now, for example, for you to build a massive prediction system with large number of points. For example, I got interested into this because how the company we founded, we build massive indices using the nearest neighbor indices in some sense. And there we could, using simply existing technology, we could build indices for 10 to the power 11 points with a query that was sub-millisecond. So there was definitely, there is a lot that can be done beyond that. So forgetting large dimension, I think putting that question differently, which makes it hard, is that is there a way to find, in a very large dimension with lots of points, can you find k closest points? Okay, and closest point might be far, but can you find those k closest points? Okay. Correct. So now then we're going into sort of this whole plethora of things where if you believe that your data actually inherently has low dimensional structure, but actually it's high dimensional, then there are approaches. And then there are those assumption-free approaches. Then I would talk about some of the assumption-free approaches. Okay. And then there's a non-parametric, because you're not assuming its function is linear in a sense. You're not putting any model. But of course, that comes at some kind of computational cost and flexibility. So it's about trade-off between these things. And then finally, it's interpretation, because it's like When you get recommendation, somebody says you're getting recommendation of Godfather because you like Goodfella, and you like Goodfella because people like you like Goodfella. That's basically the interpretation. That is why certain prediction is what it is. And of course, these things come with some kind of distributional proxy through nearest neighbor. So that helps you if you want to think about what is the variation in your or variance in your estimation or confidence. Okay, so these are the reasons why I really like these methods. Yeah. Mm-hmm. Mm-hmm. So I think you're asking me a meta question, which I'm not fully able to parse it. So let's do the following. Uh, in Let me sort of get started because I'm still sort of talking about high level. Let me sort of set the problem up. Let's sort of go through some of the things and see, and maybe you can re-ask me the question. Thank you. All right, so that it's just a high-level overview, the introduction. Now let me get started with the setup. And again, as I said, goal here is for me to provide you one simple, clean proof that is not too lossy, okay, and that's general enough. So that tomorrow, if you come across nearest neighbor question, you don't, at least you know most what's going to be right, if not exactly what's going to be right. So you may not know the constant should be 2.67, but hopefully you will know that it should be between 1 and 10. Okay. All right. So with that in mind, here is, so we're going to look at a prediction setup, which means that we're going to do regression and classification. And I'm going to try to keep this board constant to the extent possible. But I lost. So this is really long. Okay. Sorry, I'm just trying to think about how do I thought it had 4 boards, not so many. Okay, so here is the setup. Actually, sorry. Set. So we've got features and labels. X I will denote as a random variable that represents feature. Y I will denote a random variable that represents label. Assume that there is some distribution over features and there is some conditional distribution of labels given features. Let's assume that the features live in some space X. Okay, and we'll assume that X is, to begin with, separable, and it is a metric space to determine the distances, and the metric will represent as rho, that is X, and maps them to non-negative value, and it is a metric. I will also, for generality, I will also make X Polish, that is, it's complete and it's compact. Again, for all practical purposes, think of this as r to power. Okay. What else do I need? I will assume that px is, these are, okay, so let's first define y. So the label space y is r in particular. I'll assume that it comes from an interval, and let's call it y min and y max. And then these probability measures are Borel. Okay. All right. So again, for all practical purposes, things that features are coming from some d-dimensional Euclidean space. Labels are, let's say, in interval 0 and 1. If it's categorical, say 0 or 1, otherwise some value. And we have some metric over this, for example, L2. And these are Borel measurable probability measures. That means that sort of effectively they're defined over the open sets of or Borel sigma algebra of the underlying space. All right, what else do I need? Now, this, in a sense, will help us make the following definition that, in a sense, kind of very detailed technicology, but it's relevant. It's kind of good to get out of the door once and for all. If you would be interested in predicting